In this section, I will tell you a few tricks, a few signals, how to quickly see that given vectors are indeed linearly dependent. If you look at the vectors and one of them is equal to 0, then the set is definitely linearly dependent. We can easily build a non-trivial linear combination for such vectors. If we multiply the first vector with 1, and we multiply all the remaining vectors with 0, then the result is definitely 0, because the first term is 0, because the vector is 0. And all the remaining terms are 0, because the coefficient is 0. And sum of 0 vectors is indeed 0. And this linear combination is non-trivial, because it is not true that all the coefficients are equal to 0. Namely, the first coefficient is non-zero. Another signal that is often easy to use, if two vectors are the same, then the collection of the vectors is definitely linearly dependent. And also, the proof is very easy. The linear combination would be 1 times a1 plus minus 1, which can be written as minus a2, plus, and we multiply by 0 all the remaining coefficients. If a1 is equal to a2, then if we subtract them, that means we multiply one of them with 1, we multiply the other with minus 1, and we add, we get 0, and the remaining terms are 0 because the coefficients are 0. In a slightly more general case, if one of the vectors is a multiple of the other, then the set of the vectors is linearly dependent. In a more general setting, if one of the vectors is equal to a linear combination of the remaining vectors, then the collection of the vectors is linearly dependent. And also, there is one useful knowledge or property. If we have vectors from n-dimensional space, that means each vector has n components. And if we have k vectors, then if the number of vectors, here k, is greater than the number of components, the dimension of the space, then the vectors are linearly dependent. As an example, if we have, say, 3 two-component vectors, we have 1, 2, 3 vectors, and each of them has 1, 2 components. They are definitely linearly dependent. This question, whether a set of vectors is linearly dependent or not, makes perfect sense and has a reasonable answer, even for sets consisting of just one single vector. If we have just one vector, well, if we want to write it as a set containing this single vector, then the question is this set linearly dependent or not? Surprisingly enough, does make sense. Namely, if the vector is 0, then this set is linearly dependent, and if the vector is non-zero, this set is linearly independent. Here it is slightly misleading, because the term dependent in natural language means something depends on something else. Here we have just one single vector. But formally, in mathematics, this makes sense. Also, the difference of the meaning in mathematics and in natural language is illustrated by the following example. Imagine we have 3 vectors. Say, a1 will be 1, 1, 1. a2 will be 1, 0, 0. And a3 will be 10, 0, 0. And the question is, what about the set consisting of these 3 vectors, a1, a2, a3? is it linearly dependent or independent? You can stop me now for a moment and you can try yourself. Okay? You can switch me again on. Yes, this set is linearly dependent because A3 is just 10 times A2. If you want to find a non-trivial linear combination, so yeah, this is linearly dependent because if you take 0 times A1 plus 10 times A2 minus A3, then this is a non-trivial linear combination because not all the coefficients are equal to 0. And it is equal to 0 as a result because 10 times this minus this is 0 and the first one is multiplied by 0. Now, consider that we cancel A3. And the question is, what about the set having these two numbers, A1 and A2? Is this set linearly dependent or independent? You can stop me for a moment and you can try yourself. Okay, I'm back again. Yes, this set is linearly independent because no non-trivial linear combination is equal to 0. The only possibility for a linear combination of these two vectors to be 0 must be a trivial linear combination. Well, consider the following situation. You have 3 black cats. You sell 1 black cat. What you are left with is 2 black cats. Yeah, no problem. And here we had 3 linearly dependent vectors. If you sell 1 vector, you remain with 2 linearly independent vectors. And the conclusion is vectors are not cats. Yeah, and to put this in a more serious way, the term to be linearly dependent or linearly independent is a property of the set, of the collection, of the family of the vectors. It is not an individual property of each vector. The property of the set, right? So this is one set containing these 3 vectors and it has some property, linearly dependent. This is another set and it has another property. Different set, different result, no problem. Well, and linearly dependent and independent vectors, this is a very important notion because it will help us to decide whether the system of equations has a solution or not and how many solutions. We will see this later.